Did you know one of the oldest programming languages still powers operating systems, gaming engines, and even robotics? That language is C, efficient, powerful, and timeless. In this video, we'll break down C and its key features, syntax, and real-world applications to show you why it's still so relevant today. Without further ado, let's dive in. C is a procedural and imperative programming language, meaning it emphasizes a step-by-step approach to solving problems by using functions and procedures to structure code. As a middle-level language, C bridges the gap between high-level languages that prioritize ease of use and low-level languages that offer detailed hardware control. This characteristic allows C to directly manipulate memory and hardware while still being relatively human-readable, making it both versatile and efficient. Developed by Dennis Ritchie in 1972 at Bell Labs, C has served as the foundation for countless programming languages, including C++, Java, Python, and others. Beyond shaping programming languages, C has also powered tools we often take for granted, such as compilers, interpreters, and system-level utilities, proving that even decades later, C remains at the core of modern technology. Now let's move to the uses of C and explore why it's still a cornerstone in modern computing. C is widely used for developing operating systems like Unix and Linux, as well as database systems like MySQL. Its efficiency and hardware-level control make it ideal for embedded systems, such as those found in automotive systems or IoT devices. In game development, C powers performance-critical components of popular engines like Unreal Engine. It's also the backbone for compilers and interpreters that enable other languages to function. Despite its age, C's unmatched speed, portability, and influence on languages like Python, Java, and C++ ensure it remains an indispensable tool for developers working on diverse and complex projects. Let's now look at how C code is executed. C is a compiled language, meaning its code is translated directly into machine code by a compiler before it is executed. This process involves writing C code, compiling it into an executable file using a compiler, and then running the file on the target system. This allows C programs to run with exceptional speed and efficiency, making it ideal for performance-critical applications. Unlike interpreted languages, which are executed line by line at runtime, compiled languages like C produce an executable file that can be run independently. If you're curious about the differences between compilers and interpreters, check out our separate video on interpreters versus compilers for a deeper dive into how they work. Now let's break down the structure of a basic C program. A basic C program consists of several key components that define its structure. At the top, header files are included using #include, which allows the program to use built-in functions and libraries. Common examples include standard io.h for input and output operations and math.h for mathematical functions. Below the headers, additional functions can be defined before the main function to keep the code organized and reusable. The main function serves as the entry point of the program, where execution begins. Inside the main function, we write the core logic of the program, such as variable declarations, function calls, and loops. Finally, return 0 at the end of the main function indicates successful execution. This structure ensures clarity, modularity, and efficiency in C programming. Now, let's dive into data types in C. In C, data types define what kind of data a variable can hold. The most common ones are int for integers, float for decimal numbers, and double for more precise decimal values. For individual characters, we use char, and for logical values like true or false, we use bool, which can be accessed through the standard bool.h library. Modifiers like long and short can be applied to data types like integers for larger or smaller values, such as long int for larger integers or short int for smaller ones. C doesn't have a built-in string type, but strings are represented as arrays of characters ending with a null character, typically represented as \0. Additionally, C uses void to indicate the absence of a data type, such as when a function doesn't return a value or when working with pointers. These data types ensure variables are allocated the correct amount of memory and that operations are performed properly. For more details on data types and programming, check out our separate video on the topic. Now let's talk about working with variables in C. A variable is simply a named storage location for data. The basic structure looks like this: data type, variable name, value. For example, To declare and initialize a variable in one step, we can write int number equals 10. This creates a variable called number of type integer and assigns it the value 10. Alternatively, we can declare a variable first and assign a value later. For example, float temperature, and then in the next line, temperature equals 36.5. Variables can also be updated throughout the program. The number variable we declared earlier can be changed like this. Number equals 20. This flexibility allows us to store and modify data dynamically as the program runs. Next, let's explore input and output in C. The two most commonly used functions for this are printf and scanf. Printf is used to display information to the user, while scanf reads input from the user. Here's an example demonstrating both functions. In this example, printf displays the message, enter your age, and scanf reads an integer input, storing it in the variable age. Then, printf displays the entered age. Notice that scanf uses the format specifier, represented as %d, to read an integer, and the ampersand symbol passes the address of age. For more complex input scenarios, functions like fgets and getchar can be used. Let's take a look at how they work. Both are used to take input from the user, but they behave a bit differently. fgets reads an entire line of input, including spaces, until a new line character or the specified number of characters is reached. It's useful for getting strings with spaces. On the other hand, getchar reads a single character at a time, which is useful when you only need a single character input. Here's an example using fgets to read a full line of text. In this example, fgets reads the user's name, including spaces, and stores it in the name array. After the user types their name and presses enter, printf displays a greeting with the inputted name. If you only need a single character, you could use getchar instead. This allows you to handle different types of user input depending on the needs of your program. Now, let's explore operators in C. Operators allow us to perform calculations and make decisions in a program. Arithmetic operators are pretty straightforward. We use plus for addition, minus for subtraction, slash for division, and asterisk for multiplication. One additional operator is modulus, written as %, which gives the remainder of a division. For example, 10% 3 results in 1, because 10 divided by 3 leaves a remainder of 1. Comparison operators are used to compare values and return either true or false. Like in many other programming languages, adding an exclamation mark at the beginning negates the operator. For example, double equals checks if two values are equal, while exclamation mark equals checks if they are not equal. Other operators include greater than, less than, greater than or equal to, and less than or equal to. Logical operators are used to combine multiple conditions and are often used in control structures like if statements, which we'll cover later in the video. Double ampersand signifies a logical and it returns true if both conditions are true. Double vertical bar denotes a logical or, and it returns true if at least one condition is true. Finally, exclamation mark represents a logical not, which inverts a condition's truth value. For example, this condition returns true if x is not greater than 5. Building on what we've covered, let's look at assignment operators. We've already seen the equal sign used in the variables chapter to assign values, but there's more to assignment operators. Assignment operators are used to store values in variables. The simplest one is the equals sign, like x equals 5, but we also have compound assignment operators, which combine arithmetic with assignment. For example, x plus equals 3 is the same as x equals x plus 3. Next, we have bitwise operators, which function similarly to logical operators, but instead of evaluating entire values as true or false, they work on individual bits. The bitwise AND operator, written as a single ampersand, sets a bit to 1 only if both corresponding bits are 1. The bitwise OR operator, written as a single vertical bar, sets a bit to 1 if at least one corresponding bit is 1. The bitwise exclusive OR, written as a caret, sets a bit to 1 only if the bits are different. The bitwise NOT, written as a tilde, inverts all bits. There are also left shift and right shift operators, written as double less than and double greater than, which move bits left or right, effectively multiplying or dividing by powers of 2. For example, shifting 5 to the left by 1 results in 10, since shifting left by 1 doubles the number. Finally, increment and decrement operators are used to increase or decrease a variable's value by 1. The double plus operator increments a value, while the double minus operator decrements it. These can be used before or after a variable. Plus plus x increments before the value is used, while x plus plus increments after. Similarly, minus minus x decrements before, and x minus minus decrements after. These operators are especially useful in loops and iterative statements. Now, let's dive into control structures in C. Control structures are essential for directing the flow of execution in a program, allowing us to make decisions and repeat tasks based on certain conditions. They include loops, which enable us to repeat actions, and conditional statements, which help us make decisions depending on whether certain conditions are met. These structures are crucial for writing flexible and efficient programs, as they let us adapt the program's behavior to different situations. In this chapter, we'll cover both types of control structures and see how they work with examples. When talking about loops, the first one that comes to mind is the for loop. It's a versatile loop used when you know in advance how many times you need to repeat a block of code. The basic structure of a for loop looks like this. The start initializes the loop variable, the condition determines if the loop should continue, and the update modifies the loop variable after each iteration. Here the loop starts with I equal to 0, and it continues as long as I is less than 5. After each iteration, I is incremented by 1. This will print the numbers 0 through 4. The for loop is ideal for cases where you know the number of repetitions up front. Another fundamental loop in C is the while loop. Unlike the for loop, which is ideal when the number of iterations is known beforehand, a while loop is best when repetition depends on a condition being met. Its structure is simple. The loop executes as long as the condition remains true. For example, if we want to keep asking the user for a number until they enter a positive one, we can write the following. This ensures that the user cannot proceed until they provide valid input. Since the condition is checked before each iteration, it's important to update the relevant variable inside the loop to avoid infinite execution. Now let's take a look at a variation of the while loop, the do-while loop. Unlike the regular while loop, which checks the condition before executing the code, the do-while loop guarantees that the loop body runs at least once before checking the condition. This is useful when you need to execute a block of code first and then decide whether to repeat it. The structure of a do-while loop consists of the do keyword, followed by the loop body inside curly braces, and the while keyword with a condition at the end. In this example, the user is again repeatedly asked for a positive number. The loop executes at least once, ensuring the prompt is displayed before checking the condition. If the condition is still true, the loop continues. Otherwise, it stops. Next, let's move on to another important type of control structure, conditional statements. In C, conditional statements allow the program to make decisions based on certain conditions. The most basic is the if statement, which evaluates a condition and executes a block of code if that condition is true. If the condition is false, the program simply skips the code inside the if block. For situations where you want to handle multiple conditions, the else if statement can be used. It checks another condition if the previous one was false. Finally, the else statement acts as a fallback, running a block of code if none of the previous conditions are true. Here's an example. In this example, the program checks if the user is an adult, a teenager, or a child based on their age. It's important to note that else if and else are optional, and you can use just an if statement if only one condition needs to be checked. Along with loops and conditional statements, C provides additional ways to control program flow, the break and continue statements. The break statement is used to exit a loop immediately when a certain condition is met, skipping any remaining iterations. For example, in a loop searching for a specific number in a list, using break stops the loop once the number is found. On the other hand, the continue statement skips the current iteration and moves to the next one. This is useful when certain conditions should be ignored without stopping the loop entirely, such as skipping negative numbers in a sum calculation. Before we move forward, let's take a moment to talk about comments in C. Comments allow you to add notes to your code without affecting how it runs. They help explain what different parts of the code do, making it easier to understand and maintain. There are two types of comments in C, single-line and multi-line. A single-line comment starts with double slashes and extends to the end of the line. For example, this is a single-line comment. Multi-line comments begin with /* and end with */, allowing you to write comments that span multiple lines. For instance, this is a multi-line comment that can cover multiple lines of text. Using comments effectively can make your code clearer, especially in complex programs. Next, let's talk about arrays in C. Arrays allow you to store multiple values of the same data type under a single variable name, avoiding the need to declare separate variables for each value. An array is defined by specifying its type, name, and size, like this, which creates an array that can hold 5 integers. Elements are accessed using zero-based indexing, meaning that in this case, number 0 refers to the first element and numbers 4 to the last one. Strings which do not exist as a separate data type in C are represented as arrays of characters ending with a special null character. For example, this line creates a character array storing the string Alice. C also supports multidimensional arrays, such as 2D arrays, which can be used to represent matrices. For instance, this line defines a 3x3 grid of integers that can hold 9 values in total. Arrays are fundamental in C programming, making it easier to manage structured data efficiently. Now let's discuss functions in C. Functions are reusable blocks of code designed to perform specific tasks, making programs more organized and modular. They help eliminate repetitive code and improve maintainability by allowing you to define actions once and use them whenever needed. The basic structure of a function includes a return type, function name, optional parameters, and a body enclosed in curly braces. Here's an example of a simple function. In this example, int is the return type, indicating the function returns an integer. The function is named add and takes 2 integer parameters, a and b. Inside the curly braces, the function adds the 2 numbers and returns the result. Functions are called by their name, passing necessary arguments, like add 3 and 5, which would return 8. By breaking down complex tasks into smaller functions, C programs become easier to understand and manage. Now let's talk about pointers in C. Pointers are variables that store the memory address of another variable rather than the value itself. They are useful for efficiently handling memory and passing large amounts of data between functions. For example, if we declare an integer variable with int x equals 10, we can create a pointer to x using this line. Here, $x retrieves the memory address of x, which is then stored in PTR. To access the value at that address, we use dereferencing, represented by an asterisk, to retrieve the value stored in x by following the address. Pointers are essential in C for working directly with memory. If you want to learn more, check out our separate video on pointers. Now that we've covered pointers, let's talk about memory management in C. Memory management is an important part of C programming because it lets you control how memory is used in your programs. In C, memory isn't managed automatically, so you need to allocate and free it manually. Functions like malloc are used to request a block of memory, which is useful when you don't know in advance how much memory your program will need. However, malloc doesn't initialize the memory, meaning it may contain garbage values. If you need memory that is automatically set to 0, you can use calloc. If you need to change the size of an allocated block, realloc lets you adjust it while keeping the existing data. Once you're done using dynamically allocated memory, free releases it so the memory can be used elsewhere, preventing memory leaks. These functions are commonly used when working with dynamic data structures like arrays, linked lists, and buffers. Next, let's take a look at the C standard library. The C standard library is a collection of pre-written functions that provide essential services for C programs, making it easier to perform common tasks like input-output, memory management, and string manipulation. Some commonly used functions from the standard library that we've already seen include printf and scanf for input-output, and malloc and free for memory allocation and deallocation. The C standard library also provides important header files like standard input-output for file handling, standard library for general utilities, and string for string manipulation, where you'll find functions like string length for calculating the length of a string. In addition to the standard library, C also supports other libraries that can be linked to programs for additional functionality. For example, Libraries like math provide mathematical functions like sine and square root, while time is used for handling time and date functions. These libraries help developers avoid having to write common functionality from scratch, speeding up development and ensuring more efficient, reliable code. Now, let's quickly look at the advantages and challenges of using C. C is a powerful and versatile programming language with many advantages, including its efficiency, speed, and low-level memory control. Since it allows direct manipulation of hardware and memory, C is ideal for system programming, embedded systems, and performance-critical applications. The language is also highly portable, as C programs can be compiled and run on different platforms with minimal changes. However, C comes with challenges, particularly in its lack of built-in safety features, which can lead to issues like memory leaks, buffer overflows, and pointer errors. It also requires the programmer to manage memory manually, which can be error-prone and complex, especially for beginners. In conclusion, C is a powerful programming language that offers a balance of efficiency, speed, and control over system resources. While it requires more attention to detail and can be challenging due to its low-level nature, it remains an essential tool for tasks where performance and direct hardware interaction are critical. C's versatility allows it to be used in a wide range of applications, from system programming to embedded systems, and its widespread use in legacy systems ensures its ongoing relevance. Despite its challenges, the knowledge of C opens doors to understanding how computers work at a fundamental level, making it a valuable skill for aspiring programmers. This concludes our exploration of the C programming language. If you enjoyed it, consider subscribing to our channel and liking the video. Feel free to also check out our other videos on related topics. Thank you for watching.